Hello, gents, and welcome to section 3.3 on energy and work, entitled Why Airbags? So we know what both energy and work are, but in terms of our investigation, we can think of the damage to our egg as similar to the damage to a skull, our skulls during a collision. Both egg 1 and egg 2 had approximately the same mass, and they had approximately the same velocity upon impact because we dropped from the same heights. Thus, they had the same kinetic energy. Egg number 2 did not smash as egg number 1 did due to a softer landing surface. Let's talk about the significance of our landing surface. To stop the egg, the surface had to apply a force over some distance. That distance was measured by the indentation. So when we apply a force over some distance, we know that work is being done. So the surface applies or does work on the egg in order to stop it. The hard surface, we could not see the indentation there. Meaning when that egg came into contact with the hard blacktop surface, it didn't indent. It did, relatively, it did, but we just couldn't see it. It was so slight. So we saw that crash. The egg cracked. Here, the soft surface, we could see the indentation. It was measurable. So when we hit, it impacted and indented. So work was done. A force was applied over some distance, the distance that the surface gave. Now, this leads us to a very important concept: work and the change in kinetic energy and how they're related. So we'll investigate this by the question of, how does an automobile stop? So brakes first decrease the speed and effectively eliminate the kinetic energy by applying a large force over a large distance. Because of that, definition-wise, we know that work is being done. Work is equal to the force times the distance. Now, special note, in order to change the kinetic energy, we had a fast automobile and it came to a stop. In order to change the kinetic energy, work must be done. A force was applied over a distance. Thus, work is equal to the change in kinetic energy, the change. We can represent that with the formula here. Work equals the change in kinetic energy. Now, getting rid of this kinetic energy that the car has and its occupants have before collision can be done in different ways. The work that is needed to stop the car is a fixed amount, meaning the car has some amount of kinetic energy. It's going to take that same amount of energy through the form of work to stop it. So work is fixed for a certain scenario. So work can be done in two different ways. One is with a small force over a large distance. Or it can be done with a large force over a small distance. One is safer than the other. The first one is considered to be safe. Applying a small force over a large distance, this one is not as safe. Now if we compare that to our investigation, egg number 1 fell down and a large force was applied on it because the surface only moved a small distance. It did work on the egg, but only over a small distance, so the force was large. The second egg fell down, but due to the surface gave in more, meaning work was done on that egg, the same amount of work, but over a larger distance, thus the force was smaller. Now, in a collision, if we put this in terms of cars, well, look at your eggs first. In a collision, egg number 1 resembles a collision where the car and its passengers come to a stop in a small distance. If the passenger strikes the interior of the car, such as an unpadded steering wheel or a windshield, God forbid, the stopping distance will be very small because steering wheels and windshields don't give very much. They don't bend very easily. That would require a large force. A small stopping distance requires a large force to do that, which means you can have a serious injury. Thus, we use airbags to increase the distance over which the stopping force is applied. So the airbag allows you to come gradually to a stop. It allows it more time to pass, meaning more distance in which this work is being done. This reduces the force of impact, and this saves your life. So if we look at this in terms of speed and kinetic energy, we know that work is equal to the change in kinetic energy. This relationship explains why slowing down is always the best safety move. You can have your seatbelt on, you can have all this on, but slowing down or having a nice speed, slower speed, is the greatest safety move. To stop a car moving at 9 meters per second, for example, the brakes must apply a large force over about 6 meters to stop safely. What if the car was going 3 times faster? Would it require 3 times the stopping distance? What do you think? Common sense would say yes at first, but we have to look a little deeper. The answer is no. No, it would not just be 3 times the stopping distance if you increase the speed by 3. If you look at our kinetic energy equation, Ke equals 1/2 mv squared, velocity is squared. So kinetic energy is directly proportional to the square of the speed. So if I triple the speed, Ke is not 3 times more, but 9 times greater due to this squared relationship. So the work required to stop the car is about 9 times greater. And the distance over which the work is being done is 9 times greater. So if you're going 9 times faster, you need 9 times the amount of stopping distance. Sorry, if you're going 3 times faster, you need 9 times the stopping distance because you have 9 times the kinetic energy. Thus, you need 9 times the work to be done to stop you. For example, if your velocity is 27 meters per second, which is 9 times 3, you need 54 meters to stop safely, which is 6 times 9. So gentlemen, please take notes on this, and we'll talk about this tomorrow in class. Adios.